We have studied how objects move in one dimension and in two dimensions. We know how to describe the motion and the trajectories of objects with constant velocity, with constant acceleration, or even with an arbitrary acceleration. But so far, we have always assumed that we are in some sort of preferred reference frame, a reference frame attached to us or to our laboratory. Now, think that we observe an object moving with respect to us, and another observer is also studying that object's motion. What happens when this second observer moves with respect to us? Well, that other observer is in a different reference frame, and its position, as seen from our point of view, is changing. We are talking about relative motion here. How to describe the motion of an object from different reference frames. We will focus only in the case that all reference frames involved are inertial reference frames. That is, they all have uniform motion. If that is the case, there is no way for each observer to tell if they are at rest or they are in motion. There is no experiment that you can perform that can tell you that. Galileo Galilei realized this. He explained it by saying that if you go to a closed cabin in a ship without windows, you take with you all sort of scientific instruments you want, you will never be able to tell if the ship moves or if it's at rest. Assuming that the ship, if it moves, it does it with uniform motion, of course. There is no physical experiment that can distinguish uniform motion from rest. Now, keeping in mind this, keeping in mind that we are in an inertial reference frame and another observer is in a different reference frame moving with respect to us, that observer will think that she is at rest and we are the ones moving with uniform motion. When you drive in a highway, who's moving? Your car forward or the whole landscape backwards? For example, here you will see that Doctor Who's blue box and that taxicab are moving with respect to an observer which is on the ground. But because they both are moving with the same speed and on the same direction, they are both in the same reference frame.
Santa's a robot!
But we want our two observers to agree in the description of the motions of the object they are observing, right? So, well, there is a way to do this, and it is through Galileo's transformation equations. Equations that help us go from the measurements of one observer to those measurements performed by the other observer. If we look how the second observer moves with respect to us, we can describe its motion with x is equal to x naught plus vt, where the velocity is constant as it is a uniform motion we are considering. This can be generalized to 2 or 3 dimensions using vectors. R vector is equal to r naught vector plus v vector times time. Now, we want to transform our observations into those observations of the other observer. For that, we need that the position of the object as measured by us is the position of the object as measured by the other inertial reference frame plus the relative velocity times time. Driving the velocity of the object as observed by us is equal to the velocity of the object as observed by the other inertial reference frame plus the relative velocity of that inertial frame with respect to us. And if we derive again, we see that we both measure the same acceleration for the object under study. This description and equations are very important. They are Galileo's relativity and need to be accounted for when we have several objects moving at different speed, as for example when we want to send a satellite to Mars, where the Earth is moving, Mars is moving, and the satellite is moving, and each one has a different velocity.
What's the intercept range?
I'm checking. 312 meters.
Did you say 312? Great, I'll wave at you guys as I go by.
Johansson, what's my relative velocity to Mark?
5.2 meters per second.
Copy. Adjusting course.